this is a quiz problem I gave to my class. I'm going to go over the solution. This is the actual quiz, so it's a little bit small. I'm going to rewrite it on another piece of paper. I just want to show you what the picture was. I'm going to read it to you, write down the important information, and then I'm actually going to solve this 2 different ways. Okay. So here we have a dipole, a positive and negative charge, plus q minus q separated by a distance s, and this is plus 6 nanocoulombs, and this is minus 6 nanocoulombs. And then s is equal to 1 times 10 to the negative third meters. It's in millimeters. It doesn't really matter too much. And then here we have point R1 and a point 2, and I want to find delta V. Delta V equals V2 minus V1. So going from 1 to 2. So what's the change of potential? And so this R1 is equal to a magnitude of 0.02 meters, and this is 0.03 meters. But I mean, it doesn't really matter. We can put in the numbers later, and it's not that interesting. So first, let's just think, should the electric potential be positive or negative? If I have this dipole, then at this point, the electric field is going to be going this way, right? This is E, because the negative charge is closer. I'll include a link down below. We can actually calculate the expression for the magnitude of the electric field due to a dipole, especially in the far field approximation where it's far away. Along the axis, I can say the magnitude of the dipole, ED, is 1 over 4 pi epsilon naught 2qs over r cubed. But the direction we have to find out by looking at it. But here, this is a negative charge is closer than that one. So we actually have 2 electric fields. One from the negative charge going this way, and one from the positive charge going that way. But the negative is closer, so the net electric field is that way. Now that's important because as I go from here to there, I'm going against the electric field. So if I'm going against the electric field, I should have a positive change in potential. Because remember, we define the change in potential as negative E dot dl from 1 to 2. And so in this case, E and dl are in opposite directions, so that's negative, but then there's another negative sign, so I get positive. You can think of it as going uphill. Uphill, you would have a positive change of potential. I'm going against the electric field. So we can use this and this to find the change in potential. And that's what I'm going to do first. Okay, but we know it should be positive. Okay, so let's do that. So again, the definition of the change in electric potential, and this comes from the definition of work. All potentials have this negative form. This is an electric potential, which is potential energy per unit charge, but that's why it's F, that's E dot dr or dl, not F. Okay, so delta V is negative the integral from 1 to 2 E dot dl or dr, you could call it either way. Now, one of the things here also, we like to write this as a vague line integral because it could be along any path. But we want to choose a path that makes things simple. So in this case, since I have the axis is in the x direction, I can find the electric field in the x direction and integrate in the x direction, and that's going to make it much easier. And in fact, I could actually write E as the vector. I'm worried about the sign here. I think I'm just going to do it. I might make a sign error, and then I'll just ask for forgiveness later. Negative 1 over 4 pi epsilon naught 2qs over x cubed 0, 0. It's in the negative x direction. dr is going to be equal to the vector dx 0, 0. That's the step size that's in the x direction. So then E dot dr is just going to be 1 over 4 pi epsilon naught 2qs over, x cubed dx. And I can integrate that from, I'm going from, where was I going? From 1 to 2. So I'm going from x1 to x2. So delta V is going to be negative the integral from x1 equals r1, x2 equals r2. And then I have this thing, 1 over 4 pi epsilon naught 2qs over x cubed dx. Now that's something that's not too difficult to integrate because a lot of that stuff's constant. Let's pull that out front. 1 negative 1 over 4 pi epsilon naught 2qs. That's all a constant. So I just have the integral of dx over x cubed. And I can integrate that. I get negative 1 over 4 pi epsilon naught 2qs. And then I'm going to integrate this. I get, this is x to the negative 3. I add 1. And so I get x to the negative 2. So I have 1 over x squared. And then when I take the derivative, I'm going to get a negative 2. So I have to divide by negative 2. So I'm going to get this. Those two's cancel. And this is from R1 to R2. So let's evaluate this. 1 over 4 pi epsilon naught qs. That's it. 1 over R2 minus squared minus 1 over R1 squared. Now, R1 is smaller than this. So this is going to give me a positive potential, which is what I said. Yay. Okay, I'll put the numbers in. Okay, but this is actually my answer without the numbers in it. I want to do it again and see if I get the same expression using a different method. Okay, so here is my dipole. I have my plus right there. I have my minus right there. And this is R1. And that's R2. So if I want to find the potential difference, delta V equals V2 minus V1, I can actually find the potential V2 with respect to infinity. I can find V1 with respect to infinity, and then just take the difference. And for a point charge, for a single point charge, I know that the potential with respect to infinity is V equals 1 over 4 pi epsilon naught Q over R. So I also know that potential obeys superposition. So if I want to find the potential at point 2, it's just the potential due to the negative charge plus the potential due to the positive charge. And I can do the same thing for V1. So let's find V1 first. So V1 is going to be equal to, I'm going to write this as V1 plus V1 minus. That's the potential at point 1 due to the positive charge, potential due to the negative charge at point 1. So it's going to be 1 over 4 pi epsilon naught. I can factor that out. Now, I'm not using the dipole equation here. I'm using point charges. So this is going to be 1 over 4 pi epsilon naught. I can factor that out. I can also factor out the Q. And then I have 1 over R1. This is going to be 1 over this distance, right? This distance is actually going to be 1 over R1 plus S over 2. Minus the potential over here. There's a minus sign because, I'm sorry, I'm still doing, this is still V1, right? Now I need to do this potential, which is minus, because that's a negative charge, minus 1 over R1 minus S over 2. That's V1. And I know S, I know R, I know these I know all these numbers. I can find this as a number, and I'm going to. Okay. And then I can do V2 is going to be the same thing. V2 plus V2 minus equals, again, 1 over 4 pi epsilon naught Q. And then I'm going to use 1 over, it looks the same, R2 plus S over 2 minus 1 over R2 minus S over 2. Right, because it's closer to that one. And then delta V equals V2 minus V1. Now I could put it in my numbers here. I could even simplify this sum, but I don't want to do that. Okay, I could simplify this and I would get the exact same expression. But instead what I'm going to do is I'm just going to put in my numbers. I'm going to use this and this to find V2 and V1 and find the difference. And then I'm going to compare that with my other expression. And I'm going to do that. So it's a lot of calculation. So I'm going to switch over to Python. And then let's just move over here. Python. Come on. We're doing this. So right here, Python. Okay, so I'm using GlowScript VPython in Trinket. And let's make that a little bit bigger. So let's just start entering our constants. The first one I'm going to call K is 9 times 10 to the 9th. So K is your 1 over 4 pi epsilon naught. I don't want to write this out. That's the whole thing. Then I have Q equals, what did I say it was? 6 times 6 nanocoulombs. So 6 times 10 to the negative 9th. S is 1 millimeter. Where did I put that? S is 1 millimeter. So 1 E negative 3. Hopefully you can see here how awesome, you're going to see how awesome Python is as a calculator. It's much better than using a normal calculator. And then I have R1 is 0.02, R2 is 0, I did that, I did O, 0.03. Okay, so I'm going to first calculate the change in potential using my first method, which is right here. So let's just say dV, I'll call it dV1. It's the first way to do it. It's going to be equal to K times Q times S times 1 divided by R2 squared minus 1 divided by, R1 squared. I was looking at the units and thinking there's a problem, but I think there's not a problem. And let's just print this. dV1 equals dV1, and the units would be volts. I'm going to give you the code, don't worry about that. And it's negative. Where'd I make my mistake? I told you I made a negative sign error. Negative, so the negatives cancel. Final minus initial, so final is R2. Okay, I'm going to come back to that. I know the answer is 75. And I don't know why. I'm just going to put a negative sign here. I know I made a mistake. You can fix my mistake. It's a small mistake. I know it's not a small mistake, but I'm just going to move on. I could sit here all day. Okay, so now I'm going to use my other formula. Where'd I put it? Okay, I'm going to calculate V1. I'm going to calculate V2. I'm going to calculate the difference between those two. Okay, so V1 equals, I'm just going to type in my equation, K times Q times 1 divided by R1 plus S over 2 minus 1 divided by R1 minus S over 2. See, that's not so bad to type that in. I'm just typing in the equation I had. And then V2 is going to be the same thing. K times Q times 1, it's not the same thing. 1 divided by R2 plus S over 2 minus 1 divided by R2 minus S over 2. And then dV2 is the second, I'm calling dV2 the second way to do it, is equal to V2 minus V1, and then I'm going to print that. dV2 equals dV2, volts. And so you do see a difference in these two numbers, right? Because there's something that happened. The first method with the integration, I assumed a value that was an approximate value for the electric field. This doesn't use that approximation, okay? So it's actually a better answer. And it's positive. This one worked as positive. I'm still not sure why that other one didn't work as negative. But there you go. You find my error. You find my minus sign. As a homework, maybe I put it in there on purpose. Maybe, right? Okay. So there you go. 2 ways to find electric potential, change in electric potential due to dipole.